So guys, once again, we are going to transition out of reviewing this lab straight into what we're doing today. We may as well get ready for that. So periodic tables, ion charts, note-taking materials, and calculators. Yeah. But then guys, in addition to that, let's talk labs. All right, so guys, as we get into this, should you get deep enough into this editing process and you're like, oh crap, my eraser just cannot keep up with the mess that I just created, there's a ton of blank copies of this up front. Some of you are finally figuring out that because labs are weighted more heavily than homework, missing a couple points on a lab does have a pretty significant impact on your grade. So guys, you know we're doing quality work. You know this is thorough. You know I dig through these with a very, very fine-tooth comb. So if you need another copy of this, don't come up and grab it while we're talking. You can just turn your current lab into a rough draft, and you can go from there. So guys, balls in your court. Please. Hold on a second. Let me sort of mentally, yes. Okay, go ahead. Yes. Yeah. Okay, so let's talk about it. So you took the zinc, right? And you submerged the zinc in that copper 2 sulfate solution. Okay, so we know that one of your reactants then was zinc. That's a horrible Z. And then your other reactant was copper 2 sulfate, right? Cu2 or CuSO4. So what kind of reaction did you identify this as? And that's not just a guess, that's what it is. So anytime you see an element reacting with a compound, you can be pretty confident that's single displacement. Good heavens, McKay, you're struggling. Go, hurry. Yeah, so the only exception to that would be if your element is oxygen and if your compound is a hydrocarbon, then that'll be combustion. But other than that, it'll be single displacement. So Jessica, because you ask, I'll keep poking at you on this one. So this is a single displacement reaction. So as a single displacement reaction, what do we need to know in order to predict products? We need to know charges. And we look those up. Zinc is +2, sulfate is -2. So if sulfate is -2, what's copper? Is it +1 or +2? And the way that we know is we split this in half. SO4 is -2. There's one of them. This is -2, so this is +2. So that would give copper a +2 and not a +1 charge. So this is +2. Okay. Now we can reorganize these and figure out our products. So the positive zinc hooks up with the negative sulfate, and we end up with ZnSO4, and then who gets displaced? The copper. That's actually the rusty stuff that you saw in the zinc. What you actually had there was a copper coating. So literally what you did is you copper coated that piece of zinc. And so that rusty stuff that you saw in your observation was actually the copper adhering to the zinc as you were copper plating it. Yeah, yeah. No. Yeah, no, both sides. Yeah, so maybe we should talk about that. So Jessica, if that's the case, if you saw this zinc clumping onto, if you saw this copper clumping onto the zinc, what's your subscript going to be? Exactly. So that'll be a solid. But guys, no, you're putting subscripts on both sides. So guys, understand you don't get the recourse to come to me and say, hey, Mr. Knappenberger, this is what you wrote on the board. Therefore, that's what I blindly wrote down. Because guys, this is wrong. This is like -6 points if you were to turn this in. There's all sorts of things that aren't done yet. This isn't balanced. Actually, it is balanced. There are no subscripts on 3 of these 4. So understand, guys, this does not mean I'm taking these reactions to completion. It just means I'm answering your questions. Go ahead, McKay. That's correct. Yeah, so it's not like a subscript for zinc and then a subscript for SO4. But while we're talking about it, what are the subscripts? That's true, but that's not the answer to any of these. Guys, what is the subscript for for copper 2 sulfate? If you're not sure, guys, grab your labs and look at the procedure for part 5. Looking in step 1 of part 5, guys, you'll notice that it says 1 molar copper 2 sulfate. 1 molar tells you the concentration of the solution. Therefore, what's the subscript? It's aqueous. That's dissolved in water. And guys, I think we talked about this in class. Anything that has a molarity, by definition, is a solution and therefore is aqueous. So guys, as you're writing these up, it would definitely be worth your time to go back and look at the procedures, and any of those things that are aqueous, or any of those things that have a molarity, they're aqueous. So now here comes an interesting question that's going to have a huge impact on question number 6, which I don't want to answer questions about, but we can talk about it now. Guys, what is the subscript for zinc sulfate? Is it solid, liquid, gas, or aqueous? Tricky, right? The question becomes, how do you know? The answer is, you can't answer this question without a solubility table. So guys, find zinc sulfate on your solubility chart. It's all the way at the bottom. Follow zinc over to sulfate. And what little letter do you find? You find S for soluble. Guys, if something is soluble, what subscript does it then receive? Aqueous. It dissolves in water. So guys, zinc sulfate is aqueous, therefore it dissolves in water. Now guys, what if you had found the letter I in the solubility chart when you looked that up? Well, I means doesn't dissolve in water, so what would that have been? A solid, which we call a precipitate. So guys, while we're talking about this, when you write the balanced equation for number 6, there's no way that you can do number 6 without a solubility chart. Well, unless you've memorized the solubilities, which you'll do in AP. But guys, without a solubility table, you can't do number 6. So guys, what else? Other questions or things you'd like to talk about? You okay? So let me bring up a thought. Reaction number 1, equation number 1, is a reaction with oxygen. It's a synthesis reaction. What about reaction number 2? The same. It's also a synthesis reaction, a reaction with oxygen. Guys, reaction number 3 is not like 1 and 2. That is not a reaction with oxygen. So guys, let's talk about this. Looking at number 3, and this was purposeful. Number 1 and number 2 sort of lulled you into this idea that anytime you heat something up, that's a reaction with oxygen. But then guys, when we got to number 3, remember what this looked like. You had a test tube, and in the bottom of the test tube was the copper 2 carbonate. Now guys, remember what you did with this. You heated this up with a Bunsen burner. And as you heated this thing up with the Bunsen burner, you know that it gave off a gas. But guys, here's the trick. As you were heating this, some of you mistakenly said that this was a reaction with oxygen. But guys, here's the trick. The reaction took place at the bottom because you're heating this from the bottom. But guys, where is the oxygen in this poorly drawn picture? It's up in the room. Guys, oxygen is up here, the reaction's taking place down here, and this is not in contact with the oxygen. Guys, this is not a reaction with oxygen. So if you have copper 2 carbonate plus O2, erase it. Guys, it is wrong. This is actually not a reaction with anything. And guys, understand heat is not a reactant. So in this reaction, copper 2 carbonate is your only reactant. So if it's your only reactant, what kind of reaction does this have to be? Decomposition. You just took the copper 2 carbonate and you broke it apart. Now luckily you tested for what one of those products is, because you shoved in your burning wood splint and hopefully it went out, which is a positive test for what compound? Carbon dioxide. So there's one of your products, and then you just need to figure out what the other product is. So guys, one of your products is carbon dioxide. But if you take CO2 away from CuCO3, what do you have left? You've got a Cu and an O. Now guys, if you go back and do this with me, read your observations after the reaction for reactions 1 and 3. Read your after reaction observations for 1 and 3. What do you notice? What do they have in common? Black stuff, right? Number 1, the wire turned black. Number 3, what happened to the green stuff? Also turned black. But guys, if you now go and look at your balanced equations, that black stuff is the same stuff. In reaction number 1, you formed CuO by heating up the copper wire. In reaction 3, you created CuO by stripping carbon dioxide off of copper 2 carbonate. So guys, that black stuff in reaction 1 and reaction 3 was exactly the same stuff. An interesting connection. So guys, what else? Other things you want to talk about? Y'all good? Okay, so what I'd like to do then with you is one other thing. You probably aren't even here yet, but let's talk. Guys, go to the conclusion questions. So guys, looking at the conclusion questions, question number 1, what are the tests for carbon dioxide and hydrogen? Look in the procedure if you're not sure. But guys, question number 2 actually comes out of your class notes. But guys, question number 3, this is unapologetically tricky. It says, during this lab, you also carried out a combustion reaction. When did you do this? And write the balanced equation. Guys, I would encourage you to underline like 11 times combustion reaction. What I find is that a lot of students year after year get this wrong because frankly it's the last question on the lab and you're just anxious to turn it in and you just jot down something that seems to make sense in your brain, and oftentimes what your brain is telling you is not right. So guys, before you answer this question, make sure you go back and relearn what a combustion reaction looks like. Don't guess at this. Then once you understand what a combustion reaction, and it doesn't just mean burn stuff. It's way more specific than that. So guys, once you then figure out what a combustion reaction is, then you go back and think about when you did that in lab. And I'll tell you right now, it's not in the procedure. And it's also not this. Sometimes I have people tell me that the combustion reaction is when you took the hydrogen in the test tube and shoved in the burning splint and it popped. Guys, this is not a combustion reaction because this is not a hydrocarbon. So I'm going to tell you right now, the answer to conclusion question 3 is not burning the hydrogen when you tested for hydrogen with the burning wood splint. I'm not going to tell you what it is, but guys, please be careful with conclusion 3. It's more specific than maybe you might think. So, guys, now, questions? Y'all okay? You good? So you understand these are due Tuesday. Guys, please do not forget subscripts on all of your stuff in your balanced equations. Again, I'd be happy to look at these ahead of time if you want. I'm here tomorrow. Monday after spring break, they're due, so that's kind of the end of the road on that one. Yeah, let me know. So guys, are we all done with these? Okay, so slide these out of the way. Guys, out of sight, out of mind, literally bury these things. Guys, if you need another copy of the lab, I'll just leave these up here. And then guys, you need to grab something to write with and something to write on. And guys, we're probably looking at about 25 minutes of new material. And then you're going to have a chance to get your homework done. So guys, when I see you on the Monday after spring break, you're then going to have 2 things due. One will be the homework assignment we're doing today, and the other will be the lab that we just discussed. So guys, let me sort of get my life reset here, like this, and like this, and like so. All right, guys, April Fool's Day. And fittingly, today on April Fool's Day, we are going to talk about, wait for it, stoichiometry. Oh yeah. Oh yeah. Stoichiometry. It is. It sort of tickles when you say it. So guys, when you go home for dinner tonight, you're all gathered around your dining room table. Tell your parents you learned about stoichiometry, and they'll feel like they're getting their tax dollars worth out of your education. So, guys, stoichiometry is the topic. The date today is the 1st. Please don't write this down. But guys, what on earth is stoichiometry besides a really fun word to say? So guys, you got your notes titled. The date today is the 1st. Let me define for you stoichiometry. But guys, don't write it down until I tell you to. You ready? Watch close. Worked hard on this. Here's the deal. So guys, stoichiometry goes like this. Think about everything that we did in the previous unit. Guys, we did mass to mole to particle to molarity conversions to empirical formula problems. But guys, if you did the replacement test, or actually you guys all did the evaluation, guys, the only thing that you needed to learn or remember from the last unit was grams to moles or moles to grams. That's it. One-step conversions. So guys, that's this. When we say moles conversions, we just mean mass to moles or moles to mass. That's it. But then guys, think about everything we've been doing in this unit. We have been learning to write and balance equations. So guys, you ready? Watch really close. So if moles conversions and balancing equations got together and had a child, they would name that child stoichiometry. Guys, literally, that's what stoichiometry is bringing together moles conversions with balancing equations. So that then gives us the definition. It's the math of chemical reactions, and that you need to know. So guys, stoichiometry is the math of chemical equations. That's a little bit my version of the definition. It's a little more complicated, but that'll get you going. So guys, stoichiometry is the math of chemical equations. Now, as if the word stoichiometry wasn't good enough, it then leads us to a new idea, which you also want to get in your notes, called stoichiometric ratios. Stoichiometric ratios. So guys, please do not write down the definition because you don't need to know it, but you need to be able to do it. So this is a do and not a know, so don't write down the definition. Let me just give it to you, and then we're going to make sure that you can do this. So guys, stoichiometric ratios, you're not writing this down, are the molar ratios of one reactant or product to another reactant or product. So guys, for example, this, again, you're not writing this down, just watch. So guys, this is a balanced reaction. It's a synthesis reaction, nitrogen, hydrogen making NH3 with ammonia. But you'll notice that it's balanced. So guys, watch. Here's a 2, here's a 3. What's the understood number in front of the nitrogen? A 1. So guys, the stoichiometric ratio in this reaction is 1 to 3 to 2. Do you now understand stoichiometric ratios? Guys, that's all there is to it. The stoichiometric ratio is simply the numbers in front of the balanced equation, and this tells you that for every 1 mole of nitrogen that goes in, 3 moles of hydrogen go in, and 2 moles of NH3 come out. That's a stoichiometric ratio. Do you get it? Okay. So guys, if you understand that, what's the stoichiometric ratio in this combustion reaction? What's the first one? 1, 2, 2, 2, 1 to 2. You get the idea? Guys, that's it. That's the stoichiometric ratio. 1 mole of this, 2 moles of that, 1 mole of this, 2 moles of that, you're out the door. That's the only new concept that you need to understand today. You good on stoichiometric ratios? All right. And again, guys, importantly, these come from balanced equations. So this then is what we are going to do today. This you want to write down. We are almost done taking notes. We're going to solve 2 problems, and then you're going to get maybe all of your homework done before spring break, which simply means you're going to forget all of this over spring break, and we'll have to remember it when we get back together in a week. But here we go. So guys, stoichiometric chemistry, stoichiometry, is a huge subset of chemistry. But guys, of this subset of chemistry, all you need to do is learn how to solve what are called mass-mass problems. And I think it's going to be helpful for you to define this, so it's worth writing down. So guys, mass-mass problems are a stoichiometric process that allow you to predict. And guys, that's an important word. They allow you to predict how much reactant or product will be consumed or created in a chemical reaction. So prediction is sort of the pivotal idea here, guys, that when we do stoichiometry, we are predicting how much reactant or product a reaction will consume or create in a chemical reaction. So guys, as is often the case, when we look at things like this, there are steps. For this process, there are actually 4 steps. I'm going to give them to you. Then we're going to solve 2 of these. And then you guys are going to get some homework done. Not a bad way to spend the day. So guys, let me then give to you the steps. So guys, step number 1 is write a balanced equation. If only we had spent the last 4 class periods trying to figure out how to write balanced equations. Aha! So guys, balancing equations is now a smaller part of a bigger process. So everything that you've learned about predicting reactants, predicting products, writing formulas, balancing equations, guys, all of that was leading up to this day where we are going to use these balanced equations to give us the stoichiometric ratios to do the mass-mass problems. So once you've written a balanced equation, step number 2 is to convert mass to moles. That is the only essential from the previous unit. Convert mass to moles. That's why that was the only essential out of all that math we did, because we knew that you needed to be able to do gram to mole conversions because it's step 2. Then guys, step 3, and this is new, this we've never done before, you are going to apply the stoichiometric ratio from the balanced equation. And then guys, finally step 4 is the opposite of step 2. You're going to convert moles to grams. Again, the only essential from the previous unit. Only in the other direction. So guys, if you took the replacement test and you were thinking to yourself, really, these are the only essentials from that huge moles unit? This is why. You got to be able to go grams to moles. You got to be able to go moles to grams. And that's it. So guys, once you're done writing this down, we're going to solve 2 examples, and then I'm going to get out of your hair, and you guys are going to practice. You guys all caught up? You okay? How we doing? Looking good? Okay, so let me ask you a question. Guys, all of this, as the top of the page says, are mass-mass problems. Where's the name come from? Look at the steps. Guys, step 2, where do you start? Mass. Step 4, what are you solving for? Mass. Guys, that's why we call these mass-mass problems. You will always start with a mass. You will always solve for a mass. And guys, these are always the same 3 steps over and over and over. These get crazy redundant. You start with the mass. You convert to moles, you apply the stoichiometric ratio, you convert moles back to mass, grams, and you're done. So guys, these are always the same problem. So let me show you a couple examples. I don't think you need to write this down, but let's talk about it. So guys, it says how much water will be produced when 12.5 grams of methane are consumed in a combustion reaction. I'm trying to really quick in my head figure out how much methane is 12.5. So you know methane is Bunsen burner gas. So 12.5 grams is about 3/4 of a mole. So guys, this is about 15 liters. So if you could imagine about 8 2-liter bottles, that's about how much natural gas we're talking about. So if you took 8 2-liter bottles of natural gas, and if you lit it on fire, how much water are you going to get out? So guys, the first thing that we need is a balanced equation. You now have 90 seconds to write the balanced equation for this reaction. Guys, notice it's a combustion reaction. Just like I told you on question 3 on the lab, don't guess at what a combustion reaction is. Guys, grab your notes if you need. Write the balanced equation. You should be able to do that in about the next 90 seconds. Go for it. In your notes, what is this? And you'll notice I gave you the formula for methane. It's CH4. Guys, from there, this should just flow. If it doesn't, you may want to write a big old reminder to yourself to figure out combustion reactions, especially before you answer question number 3 on the lab. So guys, do this. You've been working on this for about 60 seconds. Now you have 30 seconds to grab the person next to you and together figure it out. So guys, grab the person next to you and together figure out what this balanced equation looks like. Go. So guys, you got about 10 seconds. Hey. Doesn't matter. It doesn't, yeah, I mean, 3 plus 4 and 4 plus 3 are the same thing. There's a name for that in math, right? Isn't it a community? Yeah, so either way. All right, guys. So allow me, forgive me if this is offensive, but allow me to play dumb in front of you. So guys, I have no idea what a combustion reaction is. So I go back to my notes, and I've got the rule of thumb in my notes. And it says that a combustion reaction is the burning of a hydrocarbon to always produce carbon dioxide and water. So I'm like, okay, so given that foundation, I know that it is the burning of a hydrocarbon. And that is a combination of hydrogen and carbon. Don't confuse this with carbohydrate. That's carbon and water. This is a hydrocarbon, carbon and hydrogen. But it says the burning in the presence of oxygen. So now I've got my reactants. Now guys, at this point, we need our products. And it tells us what our products always are. We don't need to balance charges. We don't need to look anything up. We just need to blindly write down carbon dioxide and water. Now guys, Colton brought up a really interesting point. Doesn't matter which one you put first. And the answer is no. You can put water and carbon dioxide. That's fine too. But then guys, we need to balance this. So we've got 1 carbon, 4 hydrogens, 2 hydrogens. So we need a 2. And then that's 4 oxygens. So we need a 2. And there's our balanced equation. So guys, notice now our stoichiometric ratio. It's 1 to 2 to 1 to 2. You guys good on that? Okay. So guys, I'm going to switch this out for the digital version of that. But this then is the balanced equation. Okay. So guys, we just did step 1. Now we need to set up a dimensional analysis grid. And guys, this we learned 2 units ago. Remember, the first thing we need is a goal. So what is our goal? First 3 words. How much water? So guys, our goal is grams of water. All the way on the right-hand side. But guys, how much water is going to be produced doing what? Burning how much methane? 12.5 grams. So guys, this is our starting point. It's the only number we've got. It's 12.5 grams. So if we burn up 12.5 grams of methane, again like 8 2-liter bottles, how much water does that make? A gallon, a drop? How much? Well, let's find out. So guys, to do this, it's the same 3 steps over and over. Grams to moles, moles to moles, moles to grams. So guys, the first step is grams to moles. And I'm just going to do it for you because this was essential from the last unit. And if that is still problematic for you, guys, this is something you've got to address. Carbon has a mass of 12.0. Hydrogen is 1.01 to 3 significant digits. Add them up. There you go. Okay, so now guys, this is the new stuff you're learning today. So we know that things have to cancel top to bottom. If moles are here, they've got to be there. So guys, down here at the bottom, please write dash moles of CH4. We'll fill in the dash in a minute. But now, guys, we need the numerator. And the numerator is our goal, which is water. So this is going to be dash moles of water. So on the bottom is always moles of your starting point. Those cancel top to bottom. On the top is always moles of your goal. Guys, now we need to fill in the spaces. This is where the stoichiometry comes in. So this is a 1 to 2 to 1 to 2 ratio. So guys, what is the number in front of the CH4 if there ain't a number in front of the CH4? It's 1. So write a 1 right there. So the stoichiometric ratio is 1 mole of CH4 to how many moles of water? 2. So we put a 2 there. That's how we use the stoichiometric ratio. Then, guys, at this point, it becomes the essential from the last unit. 1 mole of water weighs 18.02 grams. Boom. We're done. We just have to do the math. But, guys, the math is what we've been doing all along. And when you do the math, it comes to 28.086 grams. And then we get 3, 4, perfect. And by the way, the stoichiometric ratios are perfect. So 3, 4, perfect, and 4. So we get 3 significant digits. So guys, 28.1 grams. Which is about, well, it is 28.1 grams is 28.1 milliliters. So guys, we're talking about that's 30. Still a little too much. Guys, we're talking about that much water. So if we burn up 8 2-liter bottles of natural gas, that's the amount of water that you get out. About a good swallow, 28.1 grams. So guys, you good on the process? One more to go and we're done. So it goes like this. So guys, the question is, how much copper 2 nitrate will be consumed when 10.2 grams of sodium chloride is reacted with it? So guys, I don't think you need to write this down necessarily, but I would like to step you through it. So some people read this and they're like, wait, that sounds really foreign. But guys, this is actually just like the homework assignments we've done for the last couple days. Just get rid of the number. So you could even reword it this way. Copper 2 nitrate is consumed when reacted with sodium chloride. If you remove the numbers, then all of a sudden we have something that seems a little bit more familiar. So guys, in order to solve this, we need to figure out how this reaction goes. So, just like always, we write down a yield sign in the middle. Then guys, we need to figure out our reactants and our products. So how much copper 1 nitrate will be consumed? Well, guys, if it's being consumed, it's a reactant. So copper is +2, nitrate is NO3 with a -1 charge. And so +2 minus 1, we need 2 nitrates. So that would be our copper 2 nitrate. Again, guys, writing chemical formulas, that was essential from 3 units ago. It's a skill you've got to possess. Then, guys, will be consumed when 10.2 grams of sodium chloride is reacted with it. Well, guys, I hope it's okay to just know that sodium chloride is table salt and do that. Now, guys, watch how all the things that you've been learning come to bear on this. So, guys, what kind of reaction is this going to be? Two compounds going in. Classic double displacement. So guys, in order to do this, we need to know the charges. I'll switch to red. +2, -1, +1, -1. So guys, the copper +2 goes with the chloride -1. That gives us CuCl2. And then the sodium +1 goes with the nitrate -1. And that gives us sodium nitrate. Then balancing it, 1 copper, 2 nitrates, 1 nitrate. So we need a 2. Then 2 sodiums, so we need a 2 chlorines, and that balances. So guys, now we have our stoichiometric ratio, 1 to 2 to 1 to 2. Oh, heavens no. No. Was it in the previous one as well? So here's the thing that's interesting though, McKay. The reason that it was, no, the other one was combustion, never mind. There is a relationship between the charge of the metals and the way it balances. So copper's +2, this balances with 2s. You will see some relationships that way, but it's not always 1, 2, 1, 2. Yeah. And all of that was based on the idea that it's double displacement. So in a double displacement reaction, it goes positive to negative and positive to negative, and then you just you pair them up by charge. You guys good? Okay, so I'm going to switch to the digital version of this, which looks like this. Now guys, from here, seriously, these get repetitious. We need a goal, we need a starting point. What are we solving for? How much copper 2 nitrate? So guys, that's going to be our goal, and we're going to write that down all the way on the right. Copper 2 nitrate is CuNO3 Then guys, how much copper 2 nitrate will be consumed when 10.2 grams of table salt are reacted? Now guys, at this point, seriously, grams to moles, moles to moles, moles to grams. Every time, grams to moles, 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 it's always the same. So the first thing we've got to do is grams to moles. Chlorine's 35, chlorine's 23, sorry, sodium's 23, chlorine's 35.5. That means 58.5 grams is a mole. Then guys, after that, we need the mole to mole ratio. So our starting point goes on the bottom, blank moles of NaCl. Our goal goes on the top, blank moles of our goal, which is copper 2 nitrate. Now guys, where do we get the numbers that fill in the blanks? From the balanced equation. Fill them in ahead of me. You okay? So guys, the number in front of the NaCl, obviously right there, is a 2. And then the number in front of the copper 2 nitrate is blank. So that's an understood 1. Then guys, our last step is just moles back to grams. 1 mole of copper 2 nitrate, doing the math, adding everything up is 187.5 grams. Go ahead. Oh, Kyle, I'm sorry. Have you been there for a while? You had this desperate look in your eye. Go ahead.
On the right side,
yeah.
Do you even need that side of the equation to solve it?
Absolutely. Yeah, interesting. Isn't that interesting? Because you're starting with a reactant and you're going to a reactant. Do we even need the right side of the equation? And the answer is yes, because without this, we wouldn't know that this balances with a 1 and a 2. So we have to have the products in order to balance the equation, even though it doesn't show up in the math. Isn't that interesting? You guys okay? So guys, then we do the math. I have no idea what it works out to, but I did it last night. 16.346. Then we've got 3, 3, perfect, and 4. So we get 3 significant digits, and it's 16.3 grams of copper 2 nitrate. Now guys, here's the deal. I know that this is wildly abstract. You look at this and you're like, what the stink does this mean? What is 16.3 grams of copper 2 nitrate? The answer is we're going to do this in lab next week after spring break. Not this, but guys, this is going to become much more tangible after spring break because we're going to go into lab and start predicting how much product reactions should produce, and then we're going to do them and collect the product. So guys, for now, let this be abstract. Let this just be a process. And then when we get together after spring break, it's going to become much more concrete, if you will. So guys, grabbing your homework packets, let me share with you some helpful hints, and then the remainder of the day will be yours. Guys, please remember that in your homework packet, you have an assignment 2B. Guys, that assignment 2B, again, we will never address in class. It's just additional practice for balancing equations. Guys, we're going to do assignment 3. So let's go through this together. 1 and 2, I gave you the balanced equations. 3 and 4, I did not. You'll be writing them. Then, guys, 5 and 6, I gave you the balanced equation, but that balanced equation is actually for both 5 and 6. Then, guys, going down to number 7, it seems really random. It just says classify these reactions. Synthesis, double displacement, you get the idea. But guys, why did I drop that into the middle of this assignment? And the answer is because the equations in number 7 are the equations for the reactions in 8 through 13. But they're not in the right order. So guys, on 8 through 13, you need the balanced equations. They're up in number 7. You just have to figure out which one to use. And they are balanced correctly. So guys, bottom line is, this is your homework that will be due on Monday. You now have 25 minutes to work on this. I will print the answers and post them up on the wall. And guys, this is the remainder of our day. So dig in, ask questions if you need. Let's get some of these done. Go get them.